thank you for the introduction. And I'd like to thank organizer for giving me a chance to give a talk here. Today I'm going to talk about residue mirror symmetry, but I will explain the old version about Toric residue mirror theorem. And this is joint work with Professor Jeongseok Kim and Professor Kazushi Ueda and Yutaka Yoshida. So today I always assume my base field is C. So first, I want to say something about main region. So actually there are several versions of statement of mirror theorem, but I want to introduce one of mirror theorem statement conjectured by Batirev and Materov. In 2002 and 2003. So this is for hypersurface case and this is for complete intersection case. So I will explain more precisely later. And this is proved by Senesh and Perrin. In 2004. In 2006. Also this is for hypersurface case and this is for complete intersection case. Also independently Borisov proved this theorem in 2005 for hypersurface case, and Karu also proved a complete intersection case in 2006. 2005, sorry. To state this theorem, I should start with, so yeah, let this be a projective Toric variety. And y via Calabi-Yau complete intersection. So later I will abbreviate this notation C, just CYCI. Then the Toric residue mirror theorem states that Toric residue function of each mirror y hat, how can I mirror is equal to some generating function defined by using Morrison-Plesser moduli space of y. So here I should explain something. So later I will explain this quantity more precisely, but for now I should say this is rational function and this is power series. So that equality means after power series, and also Batirev explained how we choose mirror for Calabi-Yau complete intersection. So for Calabi-Yau complete intersection in toric variety. So
assuming X is smooth?
Yeah,
so
but it has it should have good singularities, but I want to avoid every singularity issue in this. But yeah, anyway, so I will explain a little bit how to choose mirror after, and also already Dr. Kim explained in previous lecture how to choose mirror for Fano toric variety, but so Giventhal and Horibapa suggest how to choose for Fano complete intersection in toric variety also. So anyway, the idea, a very brief idea of proof this theorem is using Jeffrey-Cohen residue. So they show first left-hand side equal to Jeffrey-Cohen residue of Y, and also second step is this Jeffrey-Cohen residue is also equal to right-hand side. So I want to say that this Jeffrey-Cohen residue originally come from hyperplane arrangement people. So maybe now I want to state non-toric case. So for general quotient, so yeah, this is GIT quotient of affine variety. So this should be affine variety made up by some reductive group, or it can be explained by symplectic reduction also. So yeah, if X is symplectic reduction, but not necessarily Calabi-Yau anymore, then our conjecture is some correlation function of a twisted GLSM for X is equal to generating function defined by using graph Quasiment modular space of X. So this function comes from physics. So physicists this quantity define this quantity maybe, as far as I know, last year, and this is defined by using Jeffrey-Cohen residue, and maybe so this conjecture is interpretation of this quantity from physics to math world. Maybe.
Can I ask a question?
Yeah.
So Jeffrey Cohen residue is defined on the symplectic reduction, right?
Yes.
So do you mean that Y is a reduction of a certain caliber
Yes.
or symplectic?
Yeah, it should be.
Y is?
Yes. The complete intersection can be also written as a quotient. And more general case, so this quotient is explained by GLSM in physics. This stands for KAIST linear sigma model, by the way. So our main theorem is if X is Toric itself or Grassmannian, so or more, maybe partial flag, or complete intersection in there, then the conjecture is true. That's our main theorem. So the idea of proof of this theorem is using so-called factorization formula, but it's nothing but just C-star localization and some mirror symmetry statement, and also we use abelian, non-abelian correspondence for Grassmannian or partial flag variety case. Yeah, that's a preview of my talk, but I'm not going to talk about this story. I want to explain what Toric residue mirror theorem statement is. Okay. So do you have any question? Okay. So Toric residue, to explain Toric residue, so let me begin with some lattice M, and let delta be polytope in MR, and with property that the vertex of delta is contained in M, and let SK delta be a vector space generated by monomial. Vector space. Yeah, this monomial is Roland monomial, so this is contained in here.
T from starting from T0 to Td or
Yeah.
T0
Yeah,
is
T0.
the value.
Yes.
Extra value T0.
Correct. And if we have this data, so actually if we have this polytope, then we can define toric variety. Toric variety P delta is defined by product of this.
V1, M1 is V1.
M1, sorry. Yes, M1. Yes. And now we put some final condition on this toric variety. So suppose delta is reflexive polytope. This means first it contain origin in its interior, and also the second condition is it's dual polytope, which is defined by this way. Is also lattice polytope. Lattice polytope means each vertex. Sorry. And here n is dual lattice. Yeah. So if it satisfies these two conditions, did I explain lattice polytope? Lattice polytope is if the vertex is a lattice point, then it's called a lattice polytope. If we satisfy these two conditions, then this is called reflexive polytope. Then the known factor is that the polytope is reflexive. This is equivalent to the toric variety constructed by this polytope is Gorenstein and Fan. But as I told you before, I want to avoid all singularity issues, so I don't want to explain precisely about Gorenstein condition. So now, okay, now that so I will maybe this is not good notation, but anyway, so I want to put the label on each vertex, so that each vertex has this label, so maybe it's different from this notation, so maybe I change. It's better to change this notation. Okay, anyway, then and also let me take a polynomial. Here, this monomial TVI means here VI is then now we are ready to define toric residue function. For final, So here, before I define toric residue, I want to say something about. So here now, so T0 times our F is belonging to this poly. This vector space, right? So, and also it's known that this is isomorphic to section of anti-canonical line bundle on here. So, yeah, so maybe it's bad notation for now, but anyway, so let's define now y hat as a zero locus of this polynomial. Then it's going to be Calabi-Yau. Yeah, because it's a section of anti-canonical line bundle. So this is Calabi-Yau. Okay, this is Calabi-Yau hypersurface, of course, and so now here AI is just formal variable. So residue function depends on the AI coordinate. So now I'm going to define residue function. Residue function is a function from this vector space to this vector space. So this is a vector space morphism. So this is defined by having these two properties. The first is this kernel should be this vector space. Here F0 is nothing but T0F, and Fi is T0 Ti D. Okay. And the second property is the Hessian should map to d factorial times volume of polytope. This is the definition. So I'll explain. So I'll give you some example. So let M be a G2 and polytope is this one. This is 0, 1, 1, 0, negative, negative 1. Then P delta is isomorphic to P2. And our F is 1 minus A1 T1 minus A2 T2 minus A3 T1 T2 negative 1 power H. So so the residue F of HF. So here, so we can calculate this by hand. Residue F is A1, A2, T1, T2 plus A1, A3, T2 inverse plus A2, A3, T1 inverse minus 9 A1, A2, A3, H3. And also for later use, I introduce another residue function. This is 2A3. Yes. Yeah. So please remember this last residue function for later use.
So those residue functions is determined by these two properties?
That's right. So it's we have to call somehow this definition and lemma. Yes, yes. It's well defined by these two properties. Okay. So far, do you have any question? Okay. So now, then I'm going to explain.
May I ask, so
yeah.
what is the meaning of that residue?
That's very good question. So, the name residue comes from that there is a theorem that this residue becomes sum of local gross-ethnic residue. So this is real residue actually, but you cannot see here, so it's very hidden fact. But it's
is it related to index map? Index.
That's true actually. We can make residue index map of using dual Lightning-ship. Okay. Yeah. Sorry, maybe there's some misunderstanding. Residue index means some of using Hessian. Does that mean what's definition of residue index?
You have a manifold.
Yes.
You have an index, like a Thiasing index map. And one of it is related to.
So I don't know about Thiasing.
I'm wondering how we can compute this residue by these two properties. Is there any explicit description of residue?
Actually, this residue can be calculated by hand, but
how
in general, so
is there any explicit description? I mean, formula?
there's some algorithm to compute this residue function.
Because definition does not
Yeah, definition
does not seem to have any indication of how to calculate this.
Yeah.
Definition only tells you the property.
That's right. But I think that two properties enough to calculate to make algorithm proof. So maybe we need more. Yeah. Now I'm going to explain about Morris compressor modular space. So let me begin with the fan in MR with the first skeleton is generated by this V1 to Vn. Then using this fan we can define some Toric variety x sigma, and this can be written as GIT quotient of Cn to theta r. Here r is n minus d. And let me say So this is, each vector in Cn is one-dimensional representation of this complex torus. So I want to write this space as a this way. So here rho I is, the C rho I is just one-dimensional representation of this complex torus. And now also I want to say something about that. Here the Calabi-Yau hypersurface in this toric variety is mirror to y hat defined in previous section. So this is so-called Patrirev construction, Patrirev mirror construction for complete intersection in toric, Calabi-Yau complete intersection in toric variety. So now the definition of Morrison-Placer space is, so first of all we have to choose some beta class, and Morrison-Placer space x sigma beta is rho I di this one, and rho I one-dimensional di x di beta plus 1. This is so Morrison-Placer space is another toric variety, but it's proven that graph quasi-map space defined in different way. Actually, that is moduli space, moduli stack, but it becomes this toric variety. Anyway, so this is another toric variety, and
What do you mean by C to the DI?
that's sorry, this direct sum. Yeah. Yeah. And so also we have to define Morrison-Placer class. This is product with
What are DIs?
yes, I'm going to explain. Sorry.
Or even you define it in the small DI.
So
But what is in that?
Large DI.
large DI is toric divisor corresponding to each of this one, and this is pairing. So divisor and homology class, and this product, and then this belong to this cohomology ring group. Yeah, so because time goes very fast, so I want to just mention that this is related to obstruction bundle on graph quasi-map modular space. So this is some can be interpreted as some Euler class of obstruction bundle, and okay. So let me give same example. So you remember probably by previous delta. So by using that delta, then this fan is nothing but this fan, right? So coincidentally, this is also isomorphic to P2, by the way, but in general, they are not isomorphic. So they have some relationship of mirror relationship. So let's take a beta. So actually, this is isomorphic to integer group, right? So let me take some integer beta, and here every toric divisors are hyperplane class, right? So this H stands for hyperplane class. Then Morrison Placer space X sigma D is this one. And also Morrison Placer class is 3 times H to the 3 beta. Yeah, this. Okay. Actually, this quantity is not important. Yeah. Okay. And now I'm ready to explain toric residue mirror theorem. So let's take some polynomial with n variable of degree d, homogeneous polynomial of degree d. So d is a dimension of our length of m. So then toric residue mirror theorem states that residue of f p a1 t v1 and t vn is equal to this series function. This is very non-trivial. Actually, this is rational function, and this is, so you can see rational function. And this is power series. So here, where q beta is this one. So this statement is very actually non-trivial, but yeah, anyway. So now let me finish my talk with some explanation about this example. So now let's take a P by this polynomial, degree 2 polynomial. Then the left hand side becomes this. So can you see that? Yes, so please think a little. Yeah. Yeah. And also, so I mean, is equal to 0, 1, A2, A3. But after series expansion at this point, then this becomes beta it's positive, actually positive, and 3 beta plus 1 and A1, A2, A3 beta. right? Okay. So now I'm going to calculate in right hand side. Okay. The right hand side is Q beta, and so here the Morrison Placer space is 3 beta times 2, and Morrison Placer class is 3h times 3 beta, and here if we so D1, D2, D3 and D1, that is nothing but 3h times h, right? So this is Q beta and 3 beta 1, and after put Q T1 A1 A2 A3, then this is equal to this quantity. Okay, now I stop.